Hello, everybody. Here's the talking over the PDF of the chapters 10, 11, and 14, alcohols, ethers, and epoxides out of Org 2. We'll start with a little nomenclature and we'll mix it in every once in a while as we're going along. But in nomenclature, first you have to figure out the longest carbon chain. So in this one, we have a 5-carbon chain, so it is a substituted pentane. And when we have an alcohol, it goes at the end. We drop the E and add OL, and we can either put the number of it out in front of the pentane, or we can put it in between the pentane all. So the new way of doing it is preferring to put the number here. So the alcohol is on carbon 2, so we drop the E and add OL, so it's a pentane 2-all. And then from that, we need to also put in, we have a 3,4 dimethyl pentane 2-all or 2-pentanol, whichever way you want to write it. Okay. Then we have a primary alcohol, which every alcohol has an OH off of a carbon. So a primary one has 2 hydrogens and 1 R group. A secondary has 2 R groups, and a tertiary has 3 R groups, because they all have to have that OH on them. So the next thing is the acidity of alcohols and phenols, and for that it's taking a hydrogen, an H plus, off of the alcohol to form the alkoxide. So to do that, we have to have a base that's strong enough to pull the hydrogen off of the alcohol. We know water has a pK of basically 16. So really all alcohols, give or take a little bit, are around 16 in their pK. So from the periodic table, remember we talked about in the very beginning the acids. HCl, we remember, was a strong acid. It has a pK of -7. Water is roughly 20 units higher, 16. Then ammonia is in the 36, and then methane, the weakest acid of all the acids we'll talk about, is around 50. So that means the methyl anion is the strongest base we will talk about throughout the semester. Okay, it'll take a hydrogen off of anything that we can take a hydrogen off of. So the reagents for deprotonated alcohol, one of the best ones is the hydride ion, H-, because we can have the hydrogen go grab the hydrogen of the alcohol, send the electrons to the oxygen, and we get hydrogen gas, which is going to bubble out of solution and be gone. For this, we could use NH2- or CH3- because they are also strong enough bases to pull off the hydrogen. Okay, H2 has a pK somewhere in the mid-30s. So it's equivalent to ammonia in how bad of an acid it is, how strong the conjugate base is. We can also use some factors affecting the stability of the alkoxide, or how acidic it is. The first one we have is resonance. The more we can draw resonance structures, the more we can spread out the charge. The more we can spread out the charge, the more stable the base would be. So here we have these 2 conjugate bases of alcohols. We have the phenoxide and then the oxide of cyclohexanol. And with the phenoxide, we know we can send the electrons from the oxygen into the ring. Into the ring, and we can send them around the ring spreading out that negative charge all the way around the ring. So the pK for phenol is much lower than the pK for cyclohexanol because of these resonance structures that we can draw. And then we can send it back onto the oxygen to send it all the way around the ring to get the phenoxide. There's nothing we can draw moving that negative charge in there because this carbon here is sp3 hybridized. It has a hydrogen on it. We can't send more electrons to it. Okay. The second thing we can look at is induction. If we have something with a lot of electron withdrawing groups near the oxygen, these groups pull electron density towards them, stabilizing the positive charge or the negative charge on the oxygen as it forms. So the 2,2,2 trichloroethanol has a pK in the low 12s as opposed to ethanol itself having a pK around 16. So it's more acidic because of the chlorines. Okay. The next thing is if we have a lot of alkyl groups around, we know an alkyl group is an electron-rich group. It stabilizes cations. We learned in chapter 4 in Org 1. So it makes the pK higher because it destabilizes the conjugate base. So the T-butyl group is going to have a higher pK T-butyl than ethanol by a hair. Not very much, just a couple of units, but it's still less acidic than ethanol because of that. We know we can make alcohols by doing an SN2 on a primary leaving group with a strong base. We learned that in Org 1. Or we can do the SN1 where the leaving group leaves, we form the cation, our nucleophile adds to the cation to form the protonated alcohol, and then water adds, removing the hydrogen, giving us a T-butanol. So the SN1 has to go through the cation. The SN2 is the direct displacement. We drew those mechanisms a bunch in Org 1. We know what goes into them. If you're not sure, look back into the YouTube video for Org 1 Test 3 and watch through there. We talk about what it takes to be an SN1 and what you need to be an SN2 in the different reactions. Okay. Now, for the next one here, draw a mechanism for and predict the product for the following reaction. We have hydroxide. We know it's going to be a 2 mechanism. Since it's a secondary, hopefully it's an SN2 and not an E2. But in that, we know that we have stereochemistry here in our starting material. We have 4 different groups. We have the oxygen, the propyl, the methyl, and the deuterium. So we have a stereocenter. The oxygen at the tosylate is priority 1, the propyl is priority 2, the methyl is priority 3, the deuterium, the lowest priority group, is already in back, so we don't have to worry about it. So when we draw a line from 1, 2, 3, we see that our starting material is S, so that tells us our product that we have to draw has to have a stereocenter of R. So we need to draw basically the mirror image of this stereocenter. So we can put the OH up, we can put the deuterium coming towards, going back, we can put the methyl coming towards the other one, and then we have lots of ways we can draw it. We just have to make sure that we get the lowest priority group in back to check our answer easily, and then go 1, 2, 3 priority wise, so it goes clockwise, and it does in this case. So a little review from Org 1. If we have H3O+, we can redraw it to make it easy. But the alkene, the nucleophile, goes and grabs the least electronegative atom in solution. It goes on the least substituted carbon, forming the more substituted cation. This cation can rearrange because we have that hydrogen on the tertiary carbon. So the tertiary cation is much more stable than the secondary. Then water can add to this, giving us the protonated alcohol. And then we can remove the extra hydrogen to give us the 2-methyl 2-butanol. So our final answer is that after it rearranges, because in the mechanism we formed the secondary cation, which is not near as stable as the tertiary one, so it wants to rearrange. Okay, in the next one we have the mercury acetate. So the pi bond attacks the mercury. We have two acetates on it. We kick one out, and then mercury's big, so it can go form a partial bond back to the more substituted side of the double bond. So we have a partial positive on the carbon and a partial positive on the mercury, and then water adds to the more substituted side, breaking the positive charge, which gives us the protonated alcohol. Our best base in solution is that acetate we just kicked out, so it comes in and takes the hydrogen off, and after step 1 we have this with the mercury acetate on the less substituted carbon, the alcohol on the more, and this has cemented the regiochemistry of the addition in that we formed this oxygen-carbon bond. So then the only thing that doesn't look like organic chemistry is the mercury, and the sodium borohydride replaces the mercury with a hydrogen to give us the alcohol on the more substituted carbon and the alkene and the hydrogen on the less. Okay, so it goes in the same sort of style as acidic water, but in this one it will not rearrange because we never have a full-fledged cation. The mercury stabilizes the cation, so we don't ever have to worry about rearrangements occurring. Now in the next one, the pi bond attacks the least electronegative atom, which is a boron. The hydrogen adds to the more substituted carbon right at once, so the hydrogen and the boron add at the same time. And then with the hydroxide and hydrogen peroxide, we replace the boron with an oxygen, because that's all we have around. But in the first step, we cemented the regiochemistry of the addition because the boron is on the less substituted carbon, and the hydrogen, the more important thing, is on the more substituted carbon, and nothing changes the regiochemistry in the last step. All we do is replace the unimportant boron with the OH in that mechanism, and we said we wouldn't draw that mechanism. Okay. The first step of the mechanism explains the regiochemistry, so we don't have to worry about it as we go on. So preparation of alcohols via the reduction of carbonyls. Sodium borohydride reduces ketones and aldehydes. Lithium aluminum hydride reduces ketones, aldehydes, esters, and acids and amides, everything. Okay? And then hydrogen and platinum, palladium, and nickel reduces both the carbonyl and the alkene. So that gives us the saturated alcohol, whereas LAH and sodium borohydride do not touch the alkene. They only reduce the carbonyl. So LAH reduces the carbonyl to make an alcohol, reduces the acid to make an alcohol, reduces the aldehyde to make an alcohol, reduces the ester to make an alcohol. We'll draw a mechanism in a little while for that. Sodium borohydride does not touch, only reduces aldehydes and ketones, so it doesn't touch the ester and the acid, and reduces the aldehyde and the ketone down to the alcohol. Nothing to it. Okay, we'll draw a mechanism in a little bit with that. Now we remember the preparation of diols, osmium tetroxide or potassium permanganate gives us the syn-diol. Because of what happens in the mechanism, both oxygens add at the same time. They give us the syn-diol. The peracid forms the epoxide, and then the epoxide is opened up either with acid, water, or hydroxide to give us the anti-diol, and it can add to either side, so we get to either one from the same epoxide. We have drawn this mechanism before, and we will draw it again as we're going along. If you're not sure, this is a reaction from Org 1. It's in the review for test 4 in the Org 1 YouTube videos. Okay, so predict the product for the following diol formation reactions. Osmium tetroxide or potassium permanganate forms the syn diol. We need to say that the oxygens are on the same side. And then if we add acid to the epoxide, we know we get the antidiol. Since it is the acid, the oxygen adds to the less or the more substituted carbon. It is the oxygen of the oxygen 18. Hydroxide adds to the less substituted carbon because it's a straight SN2 coming from the backside to give us the oxygen 18. And then the peracid gives us the epoxide. And then opening it up with the acid gives us the antidiol again. Okay, so here are the again review stuff from Org 1. We've drawn all these mechanisms before. If you need to look back at the videos in YouTube or in the D2L course shell for test 3 and test 4 videos for Org 1, and they can help you out. Okay, if you have any questions, send me an email and we can talk about it as we're going along.